observation point as well. So you can think of that the field at the observation point, if you're in the source region, okay, the field at the observation point will have two contributions. One from sources outside the exclusion volume, plus the charges on the wall of the exclusion volume that give rise to this term. And that term is shape dependent. And the first integral can only be done using the principal value integration concept. Okay, are there any questions regarding this? So this actually has been something of debate. People have been always debating about what the Dade-Green's functions should be, and what the Dade-Green's function, if you want to write it in this manner, what is the proper way to write it? And it turns out that the proper way to write it in this manner is that the first integral should be a principal value integral. The second one is a delta function. This gives rise to like a delta function. Okay. So the proper way to write the Dade-Green's function is actually to think of it as a distribution. That G of R prime should be the PV G of R prime plus 1 over K squared L times R prime. So you think of it as a distribution. So this has no meaning unless it acts on the current. And you have to define how you should perform this PV. And the second also has no meaning unless it acts on the current. And you have to define what L is. L is dependent on the shape of the cavity. And in the textbook, I list out different kinds of L. Okay. Let me see what I have. There should be a minus sign according to the textbook. Okay? There should be a minus sign. And then I have L is equal to I over 3 for a cube. If you use the exclusion volume to be a cube, L is equal to Z hat for a disk. And then L is equal to X hat plus Y hat over 2 for a needle. Give a needle shaped thing. And then L is equal to L1 X hat plus L2 Y hat plus L3 Z hat for ellipsoid. Okay, an ellipsoid. So you can get, this has been working out, this has been worked out by different researchers, different workers. They found L to be this. Okay? Yes?
So how do we select a exclusion volume based on the problem? So how do we know which one to use, and why don't we just all use like a sphere or something?
Sphere, this is also valid for a sphere. Okay? I guess you pick the simplest for your problem. If you do layer medium problem, you would like to do this. And if you do a general scattering problem, you might want to do a sphere or a cube, and you might do other things. But this actually is in general of academic interest. Okay, it was because people were debating what the Dade-Green's function is. And the Dade-Green's function should be thought of as a distribution in this manner. And the total will be the same. Okay, the total of the two will always be the same. The total will be unchanged, not dependent on the shape of the exclusion volume. Each of these terms will depend on the shape. Okay? Are there any other questions? Yes?
When you derive this form of the Dade-Green, you use the gauge. So if sometimes we need to use a different gauge, does that mean we have to have extra terms if we use this way to solve the for the E field?
Yeah, the gauge will not change the form of the E field. I wrote down the expression for the E field at the final end.
Yeah.
That final form does not depend on the gauge. If an extra term coming from somewhere, it always cancels, and then that third term from there. Just an A and C will be defined differently, depending on what gauge you have. But the final form of the E is gauge independent. Okay. But when we write E in this manner, we always say this is coming from A. This is coming from phi, red phi. Right? You can identify. This is also called the Lorentz gauge. The gauge that we use to get the arrive at this is called the Lorentz gauge. Okay. The final answer should be gauge independent. So, okay. Then let's look at other ways we can solve for the diagonal Green's function. And I like to go through the vector wave function approach. Okay, in finding the diagonal Green's function. I sort of talked about this in the waveguide theory course last semester, but for some of you this would be repetition, and for some of you this would be new. Okay. So the idea is that we want to solve for the diagonal Green's function to solve this problem. Mu j of r is something of this form. And then our diagonal Green's function should be the solution to this problem.
Are you defining a minus or not?
I'm defining what?
We usually define it as a minus delta function, right?
No, the diagonal Green's function always has a plus sign as a member. Okay, only the scalar Green's function has a minus.
Why the sign convention?
It's convenient, then you don't have to carry the minus sign around for the scalar Green's function, and then this is just defining this way for convenience. Okay. So then you can show that if you write E, if this is true, okay, if you write E of R to be equal to I omega mu G R prime dot J of R prime D R prime, you can show that this equation always satisfies the first equation by simple substitution. Okay, I won't go through the substitution, but you can substitute this back and show that these three equations are consistent with each other. Okay. You want me to show that, or is it generally acceptable? These three equations are consistent with each other, and that this is a defining equation for diagonal Green's function. Okay, this is a defining equation for the diagonal Green's function, and all diagonal Green's functions should satisfy that equation over there. There are other approaches in finding the solution to that equation. Let's go through the vector wave function approach in finding the solution. In this approach, we use eigenvalues and eigenfunctions from another problem that is very similar to this problem to expand the unknowns, E. So we actually would look for solutions to this equation. And we can think of this as eigenvalue of the problem, and this as our eigenfunction. So you can think of this as a matrix eigenvalue problem, like A dot x is equal to lambda x, where k squared is the eigenvalue. So there's this kind of analogy. Okay. It turns out that in order to solve this problem in a homogeneous space, you can think of a homogeneous Cartesian space to begin with, to make things simpler. Then a general way is to solve this problem with a pilot vector M. R is equal to curl of C of psi of R. Okay, one way is to let F F can be something of this type. Okay, F is something of that type. And C can be a pilot vector. C can be, for instance, Z hat. Can be, for instance, in some problem you might want to choose it to be X hat or Y hat. Okay, but for many problems we would want to use Z hat. Then if C is picked to be Z hat, then this is transversed to Z. Okay, this is transverse to Z. To C or Z hat, if C is equal to Z hat. And there's a very easy way to generate the solution to the above eigenvalue problem. And if I substitute into the above, if I pick M to be something of this form, then it must be curl of C psi must be equal to K squared curl of C psi. Right? And then I can exchange the order. Take this, since that these are all in Cartesian coordinate system. Okay, C is a Cartesian vector. I can exchange the order of differentiation. Okay, and put this all the way outside. Curl of. Let me see. This is not a good way to say it. Okay, let me use that identity first and convert this into gradient of the divergence of curl of C psi. Okay, minus the Laplacian of curl of C psi is equal to K squared curl of C psi. Okay, what is this term equal to? 0, right? So then this equation is satisfied. Now I can exchange the order of this very easily. This equation is satisfied and this equation is satisfied. Okay? I impose the fact that I want psi to satisfy this equation. So this is again another eigenvalue problem. Want to think of it that way. These are the eigenfunctions and eigenvalues. If I solve this problem, then if I construct my M will solve this problem. And then I find an eigenfunction of this vector wave equation. Okay? So this is one approach. But I can also define a second vector wave function called N, which is 1 over K curl of M. You can easily show that if M satisfies the vector wave equation, N should also satisfy the vector wave equation, because if you take the curl of N, it will be 1 over K curl of M. But then that piece over there would be just 1 over K curl of K squared M by definition. Okay. And then it will be K squared N, and hence the N also satisfies the vector wave equation. So you can construct an N very easily. Once you find an M, you can construct an N immediately by taking its curl. Okay? And then you can construct a third one, also called L, which is the gradient of psi. Okay, gradient of psi. And this L has a property that it always makes the first term go to 0. If I define the vector wave function f to be of this form, this is the second form. Okay. This is the third form. If I define my L to be of that form, then my psi always comes from this equation over here. Okay? Then it always makes the first term goes to 0. Then what is the eigenvalue that corresponds to this L? K squared is equal to 0 in this equation 1. Okay? But K squared is not equal to 0 in this equation 2. Okay, you take solution from this equation. There are infinitely many of them. You can construct infinitely many L that actually lies in the null space of this operator. This is a curve operator. It has a big null space. That null space is filled by L. So there are three kinds of vector wave functions you can construct: M, N, and L. L is always in the null space of this vector wave equation. You can think of this as an eigenvalue problem. So this thing has a big null space where lambda goes to 0. This huge null space. And that null space is filled by L. And we will use this, all the eigenfunctions of this equation to solve for the solution of this equation. Okay, we'll do that after the coffee break. We take a break and then come back to solving this equation using the vector wave functions we have constructed in this manner. Any questions so far before we take a coffee break?
You can always take the curl of the, you can take the curl of the n, right? Like
Right.
I mean, like after the, and you can take the curl of the n, like it's
Right.
still be the solution.
Right. Curl of n would be m. Again, you can prove that very easily. Curl of n, okay, by this definition, is equal to 1 over k curl of m, right? But by definition, m is a solution already.
Okay.
So it's equal to k squared m, right? So curl of m is over k. So this relationship is also true. M is equal to 1 over k over n. So they're mutually related in this manner. Okay. So once you find n, you can find n. Once you find n, you can find m. But L is a different class by itself. L lies in the null space of this operator. And this equation. Okay, any other questions before we take the coffee break? Okay, let's take a coffee break and come back and look for the complete solution to this problem.